Okay, welcome back to Elements of Calc 2. So we are looking at another example in 11.2. We're going to calculate a mean. We're going to figure out some standard deviations, figure out some probabilities, and determine a median. Okay, so we have a word problem. It's not really a word problem. It's a problem with words in it. That clotting blood, okay, clots in as a probability distribution. It looks like f of x equals 1 over the natural log of 20 times 1 over x, as long as x is somewhere between 1 and 20 seconds. Okay, so the first question I'll say is, what is the mean clotting time? So what is mean clotting time? Okay, what is the standard deviation? Okay. What is the probability that it clots within one standard deviation? So what is probability that it clots within one standard deviation? Okay. And then what is the median clotting time? Okay, so there we go. I hope that this is an actual realistic thing, but I got it out of your books, but I don't know. It didn't have a source to it. Okay, so what is the mean clotting time? So if you remember what mean is equal to the expected value of x, which is the integral over the whole domain of x times f of x. Our whole domain goes from 1 to 20. So this is going to be integral from 1 to 20 of x times 1 over natural log of 20 times 1 over x. Conveniently, the x is canceled. So this is just going to be the integral from 1 to 20 of 1 over natural log of 20. Natural log of 20 is a constant, of course. The x is canceled times my dx here. So we, pardon me, just end up with 1 over ln 20 times x as x goes from 1 to 20. This is just 1 over ln 20 times 20 minus 1 equals 19 over the natural log of 20. Okay, so that's my mean time. All right, if we go back to here, we can have a calculator on. Let's go ahead and clear. So we're going to say we have 19 over ln of 20. I'm sorry, 20. There we go. So we'll go ahead and enter that in. Come on, 6.34. Okay, we're going to hang on to that number just because the next part 2, is we need the variance. Okay, we need the standard deviation, but if you remember, we need the variance first because the standard deviation is the square root of the variance. So what we're going to do is we're going to figure out e of x squared minus e of x squared, and that's going to be equal to my variance. Okay, so let's figure out e of x squared. So that's going to be the integral of x squared times f of x over the whole domain. So that is equal to x squared, integral from 1 to 20. Okay, and we have 1 over the natural log of 20 times 1 over x. Well, some stuff cancels. So we actually end up with the integral of 1 over ln of 20, because natural log 20 is a constant. It can float through the integral sign. We have x squared over x. We just have an x, and then we have a dx, 1 to 20. Go ahead and integrate this thing out. So we have 1 over ln 20 times x squared over 2. Again, going from 1 to 20. I'm going to go ahead and rearrange some things. We have x squared over 2 natural log 20. If you remember, there's a natural log property that says natural log of a to the r was equal to r times the natural log of a. Just going to go backwards and say that we have 2 ln 20 going backwards to the ln of 20 squared. 20 squared is 400. So we're going to say this is going from 1 over natural log of 400, and then we have 20 squared minus 1, plugging this back into the integral. 20 squared we just talked about was 400. 400 minus 1 is 399 over natural log of 400. So we'll go ahead and plug that in. That's going to be e of x squared, right? That's what this is. All right. So we're going to go ahead and say that. Now, remember that the variance, right, is equal to sigma squared is equal to e of x squared minus e of x squared. We just calculated this number, right? This number was 6.34. So when I go to my calculator, I'm going to go ahead and square that number right away and say, let's go ahead and square my previous value. The last answer I had here, 6.34 squared. We'll go ahead and say, okay, that's 40.2245. That's fantastic. So if we go ahead and calculate that, we're going to say, okay, we need 399 over the natural log of 400 minus this e of x, which we just calculated. This is going to be 40.225. Okay. So I'm going to say, okay, we need 399. How about this 399 divided by, I want my natural log of 400 sitting here. Okay. And then we already squared this number. So what I'm going to do is just subtract the answer, because that's the answer that's sitting in memory. Don't do that. No, quit. Okay. Minus what my last answer. There we go. Okay. So fingers are crossed. Hooray. We have my variance equals 26.369. 369, we'll say 3. Okay, and that's my sigma squared. I don't really want that. I want the standard deviation, which is the square root of this thing. So we're going to take the square root of 26.693 or 369693. Okay, the last number I calculated. So that's going to be second function square root, second function answer. Okay, and we'll go ahead and say, boom, 5.135. So this was 5.14. That's my standard deviation. Okay, the next thing I want to do is I want to figure out what numbers are within one standard deviation of the mean. So we're going to say, what was my mean? My mean was 6.34. So we're going to say 6.34 minus 5.14, 6.34 plus 5.14. Just saying the mean minus the standard deviation, the mean plus the standard deviation. Those are the values that are within one standard deviation of the mean. So we have 6.34 minus 5.14. I'm just doing this to new decimal places. We'll say that's 1.2. Okay, and now we have 6.34 plus 5.14. Okay, so it's 11.48. Okay, so when I want to figure out what's the probability that those blood clots within one standard deviation of the mean, what we're going to do is we're going to do this integral between 1.2 and 11.48. But, as a better idea, we're going to go back and say, what was my capital F of x? And this is just the integral of 1 over the natural log 20 times 1 over x. That was our original distribution, remember? So this is going to be, 1 over ln 20 times the integral of 1 over x is natural log x. We're going to say natural log of x here. Okay, so it is ln of x over the natural log of 20 over the range of 1 through 20. So that's my capital F of x. So in order to figure out the probabilities here, we're going to say, okay, we want f of b, capital F, minus capital F of a. This is going to be the natural log of, what's my big number? It's 11.48. I'm sorry, it's not. Yeah, 11.48 over the natural log of 20 minus the natural log of 1.2 over the natural log of 20. And actually, I could even do one better. I could say, let's do 1 over natural log 20 and then say the natural log of 11.48 minus the natural log of 1.2. and figure it out that way. Okay, that'd be a little bit easier on the buttons here. So natural log of 11, okay, minus natural log, where are we, of 1.2. Okay, we'll go ahead and say equals to that, and we'll divide this whole thing by the natural log of 20, divided by ln of 20. All right. And remember, if this was a normal distribution, it would look like 68%. This is not a normal distribution. So we're looking for a probability. This we got 0.7538. Okay, again, going back to CRC books, they always go to 4 decimal places. We'll go to 4 decimal places. What this probability distribution looks like, I know what 1 over x looks like. Something like that. We're going from 1 to 20. Really, this went from, we went from 1.2 to 11.48. So we went from about here to about 11.48. We got this probability here. Okay, that area under the curve. Okay, since it's a number less than 1, I'm going to have to assume it's true. Okay, I don't have any other reason to think it's false, but I know I didn't mess up because I know I have to have a number that's bigger than 0 but less than 1. All probabilities have to be between 0 and 1. Okay, if that's not true, if you end up with a probability that's bigger, you lose a lot of points. So if you tell me the probability is 1.2, oh, I take a lot of points off for that. So make sure it's between 0 and 1. All right. The next thing they had to figure out, all right. So we had to figure out, we figured out the probability that was within 1 standard deviation. What's the median clot time? Okay. So what we're going to do is we want to integrate 1 to m of this f of x, and we want this to equal 1/2. Okay. Well, we already integrated the f of x. We already got f of b. This is going to be the natural log of x minus the natural log, well, we'll say natural log of m minus the natural log of 1 all over the natural log of 20, going with the fact that we previously had just integrated this thing. Okay. So we can go ahead and say that. Conveniently, what's the natural log of 1? You can use a calculator, it's fine. Natural log of 1, 0. So we have the natural log of m over the natural log of 20 equals 1 over 2, because we're trying to find the median. So the natural log of m, right, is equal to 1/2 natural log of 20. Okay, we could do one further. We could say the natural log of m is equal to the natural log of the square root of 20. Okay, why would I do that? Because now they're both in natural logs and we can unlogify it. It's not a real word, I made that up. Take the anti-log, it's the proper way to say that. But this is how you undo a logarithm, right? E raised to the natural log, that gets rid of it. So we have median equals the square root of 20, and that is the time at which half of the blood will clot earlier, half of the blood will clot later. So just as a thought to say, let's put a number on this thing. So we just want the square root, there we go, the square root of 20. Oops, sorry, 20, not 2. There we go. And we'll go ahead and say that, and we'll say that the median time is 4.47 seconds for the blood to clot. Okay, I hope that was a helpful example for everybody. That's everything I could possibly ask you for this whole kind of series of questions. They are approximately this hard as far as the integrals go. They don't go off and say, what's the weirdest and strangest integral I can throw at you. We don't do that because there's a lot of stuff to do. So most of them are polynomials or problems that look like this. Okay, so I hope that was helpful to you. I'm going to say thank you very much for watching the video and good luck studying for everybody. I hope everybody has a good day post-Thanksgiving. I hope you're not working retail today because that's awful. Okay, take care.